Hello, we're Team 19. Today we're presenting Project 3, Industrial Robot Survey and Design. My name is Andres Ancarola.
Rodrigo Arredondo.
And I'm Oliver Gibbs.
For the first part, I'll be talking to you a little bit about the survey. An industrial robot is a reprogrammable multifunctional manipulator designed to repeat a given task through variable program motions. Typical applications of industrial robots include welding, assembly, painting, packaging, and testing. Why are robotic solutions used? They're used because robots exhibit a much higher joint capacity and number of axes than humans. Their working envelope is higher carry capacity, they have pinpoint accuracy and speed. They have repeatability with exponentially less fatigue and biological degradation and nearly an infinite increase in tolerance for fatigue. A little background about robotics. George Devol applied for the first robotics patent in 1954. He is considered by many to be the father of robotics since he created the first industrial robot. The first industrial robot was called Unimate. It was made in his company called Unimation, which he co-founded with Joseph F. Engelberger in 1956. Now, Rodrigo will explain to you a little bit about this robot.
Like Andres was saying, this is the first robot ever created, the Unimation. It was created on 1961, and it was mainly used for quenching in the automobile industry. Right now, for the present, this is mainly what it's used. It's a 6-axis robot which is holding the piece to be deburred, and you have the deburring tool, as you can see right here, and the robot moves around it, deburring the necessary edges. This specific model is the SK16, and it is created by the Yaskawa Robotics. Now, for the future, what it's aimed at is actually making the part to be rendered in a 3D program. Then you feed it into a computer that will tell the robot where it has to move, as you can see in this video right here. This particular robot has 15 joints, and as well as the previous robot, it was made by the Yaskawa company. And here is another example that we have here. The robot is grinding a gear, as you can see in the image. And in industry, the most common types of robots used are the Scare and the Cartesian, and this is due that they can move in a 3-dimensional manner instead of a 2-dimensional manner, and most applications these days are in 3 dimensions. And another reason is the work envelope is large and is very flexible. You can do a variety of things with it. And now here's Oliver to talk to you a little bit more about robots.
So another successful robot design is seen here. This is a factory automation for industrial robots. This type of this robot is found in foundry installations for metal manufacturing. And this robot is a robot worker. It's a humanoid type robot, and these robots are more like what you'll find in the future. They can perform a multitude of tasks, such as deburring, because of their many joints and their flexibility. In summary, future robotics. In the future, larger, integrated, smarter robots may replace the numerous models used today, improving efficiency, cost, and more sophisticated end effectors, and advanced image recognition software coupled with artificial intelligence. Now we have Rodrigo to introduce you to our design project.
So for our design project, we decided to do 2 tasks, which will be deburring a star-shaped and an I-beam shape out of material. Now, we had 3 designs that we could use. The first one be the 3R robot, then we have the PRP robot, and then we have the PRR robot. The first one that we looked at was the PRR robot, and we decided not to use this one due to it's not very flexible and it cost a lot of singular points for our application. The second one that we looked at was the PRR robot, which is a little more flexible than the previous one that we just showed, but it still had a few problems with singularity points. So that's why we decided to go with the 3R robot. It's the most flexible out of the three. The only drawback is that it's very large, so you will have to need a very large work area. The good thing about this robot is very flexible, like I just mentioned, and its work envelope is very large, which allows it to do a variety of applications. And now Oliver's going to talk to you a little bit more about our application.
So for the shapes that we chose, the star and letter I, we had dimensions as follows. The max width for the star was 40 centimeters, the max height was also 40 centimeters. The max width for the letter I was 30 centimeters, and the max height was 40 centimeters. So given these dimensions, the robot would have to trace out, would have to design a workspace large enough to trace out these paths in order to deburr the parts more effectively. So our constant parameters here are the link lengths 30 centimeters for A1, 2, and 3. We chose this because it seemed like the most reasonable to reach our workspace. Really, we could have played with the link lengths more, but these were easier to work with. So for the end effector path of the star, we have all the points indicated here, and that's the shape that the robot will trace out, deburring along all these edges to remove any sharp corners. And here are the X and Y coordinates of these points. So using Excel, we were able to do an inverse kinematic analysis to obtain the absolute joint displacements phi1, phi2. And for both closures, there's two closures, 1 and 2. Here are the plots for these joint displacements. Up on the left, we have joint 1, we have joint 2 here, and this is joint 3. And these are in respect to the end effector path. And you can see both closures indicated on joint 1 and joint 2. Notice also no singularity points or positions. Now here we obtained also the relative joint displacements for phi1 and phi2. And by solving forward kinematic problem with respect to displacement, joint displacement, we were able to obtain a closure 2 here had better results for our robot, so we used that. And we uploaded these points into RoboWorks software, and RoboWorks was able to simulate the motion seen here, which is as we determined the star. And the end effector traces out the star points as given in our initial statement. Now I'll have Andreas here to talk to you about the next shape, which was the I shape.
So here we have the end effector positions for the I shape. The robot began at point position 1. It traced a symmetrical I-beam shape all around. Here we have the displacements, the absolute joint displacements for that shape, for closure 1 and closure 2. Here we have the plots, the graphs, joints 1, 2, and 3 versus the end effector path. As you can see, as is evident in all these plots, there were no singular positions. We have relative joint displacements, where both closures produce satisfactory results for phi1, 2, and 3. And we have an animation of the I shape being traced by the robot. It begins at point 1, traces the symmetrical shape, and closes again at point 1, indicating that the data was effective and accurate, and that the shape goes through its rounds effectively. In discussion, for these particular tasks, the 3R robot was more than sufficient. The choice of the design was based in part on the 3R robot's flexibility and range. If space is an issue, however, PRR design would have been considered. In conclusion, within the given field of deburring, automation, a wide range of robots and applications were studied. Jobs can vary, so adaptability of robots is essential. Given two tasks, a 3 degree of freedom robot was kinematically designed. The only drawback, however, is that only 2D planar geometries are possible. Thank you for your time. We are team number 19. I hope you enjoyed the presentation.